Good day, guys. Oh, sorry. If turns out the announcement that I was supposed to make did not get through. Announcement Kusana was that I don't want you guys to go to school because of the whole transport crisis we're having right now. Because I'm supposed to just record it. But apparently that fell. Why I really do apologize. Right now, what I want to do to make it up to you is for this video, um we'll have practice session, all 10 problems, all of the ones that for our topic last time for 1 and 2 populations. The next video will have what I was supposed to teach you guys, variances, right? So variance testing, so I-squared test and the F test, that kind of thing. For now, we'll have gauntlet of 10 problems, 10 hypothesis testing. Now, before we begin, I also want to share with you that as per our agreement, you will have a formula sheet. This is the formula sheet I will give you. Note that this looks like it's one page. Gagawin ko na lang is I'll cut this in half, cut the size in half. So each page of a bond paper will have 2 copies here. I'll just hand them off to you as you need them. This will have all of the null hypotheses here. We'll have the corresponding test statistic use, then also the remarks. The remarks as what you should do, what the degrees of freedom are. For example, in here it's v equal to n minus 1. It will most likely always be n minus 1, but you're never going to be able to fully know, especially for the more complicated ones, like the ones for 2 samples right here. It's never really minus 1. So anyway, right? We will do is that we will reference this, of course, reference this uh, help sheet, what I elect to call it, help sheet right here, here for 1 sample, and then for begin then. Begin. An electrical firm manufactures light bulbs that have a lifetime that is approximately normally distributed. Okay, immediately telling us what the test statistics should be, the normal distribution. Therefore, we're going to look at most probably the z score, the mean of 800 hours, a standard deviation of 40 hours. So it seems that this electrical firm is already telling us what the standard deviation is, because most likely this will be the hardest part in many of these testing questions. You don't know what standard deviation is. Test the hypothesis that mu is equal to 800 hours against the alternative that it is not 800. So it can be either higher, lower than 800 hours at a level of 10% level of significance if a random sample of 30 bulbs has an average life 780 hours. Okay. If you've forgotten how to do this, right, what I will need to see in your solution before I mark everything full points are 6 things. For one, what is the test statistic you're supposed to use? For two, what are your two hypotheses? For three, what is your level of significance? For four, what is your critical region? For five, what is the computation? For six, what is the judgment or the conclusion? Now, it might seem like a lot of this is just writing down givens. Yes, it is just writing down givens, right? In this case, you can write down as well the mu and then the blah blah blah, everything top. But what I need for full points is just these 6 things. Okay, so what we'll do is here number one. Let's immediately start off with our test statistic. We already know our population standard deviation. That means that our test statistic will, of course, be just the normal distribution. X minus mu over sigma divided by square root of n, which is also here. And now, letter B, we will have our hypotheses. First, null hypothesis, ibig sabihin dapat walang nangyari. In case we say mu is equal to 800. This is what we, or rather, this is what the firm is asserting, that the average lifetime is going to be 800 hours. Of course, we want to test it against our alternative hypothesis, which says that it is not 800. We're not concerned with if it's higher or lower. We're just concerned that it is different at all. So this is exactly what I want. If you guys are more particular, I would recommend putting the units in. And I suppose I should put here as well the givens. I suppose we'll have, of course, a mu hours, have a standard deviation of 40 hours. Then we have um, current sample, right? Sample average life of 788 hours with a sample of 30 light bulb light bulbs. And of course, I should also write down in here the level of significance, which is 10%. That is quite big, actually. Now, speaking of level of significance, let's also write down in here at 0 0.1. Finally, we will now have your critical region. Now, in here, as you may see, it is absent from your help sheet. That is intentional. I don't want to feed you all of the information. I want you also to just, think about what the critical region looks like. What that means basically is just, where will you be able to say definitively that you will accept or reject the null hypothesis? Because this is a normal distribution, we know likely where this critical region is. For example, we have a close enough. We have um, a normal distribution right here. We have a bell curve. Because this is a two-tailed hypothesis test, right? We don't care if it's higher or lower. What we just want is a cumulative area of 10%. We know that all of the area in this bell curve, under this bell curve, is 1 or percent. Need 10 means 5 both sides. 0.05 on the right side and 0.05 on the left side. We're now going to do is that we're just going to ascertain where that is. And I don't have my tables right here with me quickly. So go to, and we'll just find 0.05. 0.05 is exactly in the middle here, negative 1.64, negative 1.65. So the middle of that will be negative 1.645. Okay? One is negative 1.5. That means that because this is symmetric, the other side will also have 1.645. That means that your critical region, your Z, be either bigger than 1.645 or smaller than negative 1.5 for us to be able to reject the null hypothesis. Speaking of, try and calculate for this now. 788 minus all over 40 divided by square root of 30. Put this together in our calculators. See, 40 divided by square root 30 gives us an answer of negative 1.643. Ouch. Okay, so we're riding here in this region wherein it's just a little bit off. But notice that what we've done essentially is that we've cut this off between 1.64 and 1.65. Is there any way we can ascertain for sure if this really is inside or out? Because currently, based on our very crude average, right? We're just averaging things because we know that somewhere in there is that 0.05. this will not enough for us to reject the null hypothesis because one negative 1.643 is just a little bit to the right of that critical region. So let me put this now in my calculator, right? If you remember, there is a way for us to understand what negative 1.643 means in here, or rather what the area for that is going to be. So what I will do now is that I will go the p function in my calculator and then going to 788 divided by 40 divided by the root. I will now get is check check p of this value 788 40 divided by 30. It appears that the answer in here is 0.050174, which basically means this p function right here essentially doing this based on the bell curve. It plots negative 1.643 and then it tells us that this area right here is going to be 0.05017. It is really close, does not belong in that critical region right here. So for your final answer, for your conclusion, we will fail to reject H, even though it's really close. Thing is, fail to reject it because again, if you want to repeat this to yourself, you may. There is not enough evidence for us to be sure, right? And sure here means a 10% chance of being wrong. Because we are choosing to fail to reject the null hypothesis, we're saying to ourselves and we're saying to manufacturers, we're saying to those who are willing to read here our results that we are not sure. We are not sure that this is going to be significant enough of a difference for 800. We're saying it is essentially is that we're not 90% sure. We're only just a little bit less than that. And that is not significant, not statistically significant. Okay? That is your number one. From here, we're going to speed up a little bit. We're going to make this a little bit more mechanistic so you guys understand that there is a flow. It is claimed, quote unquote, it is claimed automobiles are driven on an average more than 20,000 kilometers per year. Thus, this claim 100 randomly selected automobile owners record the kilometers they travel at a 0.0, oh my goodness, at a 0.005 significance level. Would you agree? This claim, the random sample showed an average of 23,500 kilometers. A known population standard deviation, okay, a known population standard deviation of 3,900 kilometers. Now, let's try this out. We have essentially 20,000 kilometers per year. Then we have a known population standard deviation of 3,900 kilometers. Then essentially, our X bar in here, the sample average, shows 23,500 kilometers. Oh, of course, it is bigger than, but now we want to know if it is statistically significant that it is bigger than. Note that in this case, we have 100 samples, and then we have a very tiny level of significance, which means really significant, of 0.005. We mean to say here that we want to be 99.5% sure that we are not wrong. And there's this key word phrase is very important, more than. This tells us that you don't want it to be lower than. That means we should begin immediately. Our test statistic is just the z-test. Is x bar minus sigma divided by squared. Letter B. We'll now have our hypotheses. We know that The null hypothesis is just nothing changes, walang nagbabago. Right? Mu is equal to 20,000 kilometers, but alternative in here is going to be bigger than 20,000 kilometers. Kasi sinabi nila, right? More than 20 kilometers per year. Okay? Now, letter C. We will have is our level of significance, which is 0.005. Letter D, we need to have a critical region wherein your Z value needs to be bigger than 99.5%, or just if you're going to think about it this way, because the area of the normal distribution is symmetric, you're just gonna have is the positive version wherein the corresponding value 0.005. It is in between these two. Negative 2.57 and negative 2.8, negative 2.575, or in this case, positive, because it needs to be on the other side. Oh, 2.575. Go. And then let's have our computation. Letter E, D equal to 20,500 minus 2,000 all over 3,900 divided by square root of n is 100, which is just 10. So we will have 3,500 minus 1,000 over 3,900 divided by 10. This gives us a value of, oh, I see. That's quite noticeable, 8.974. There you go. What else can we do in here? I guess we are really, really sure then, therefore, that we can reject the null hypothesis. Congratulations. That is way, way far. That is way, way far. Just so we can see a visualization of this, this is our bell curve. Our bell curve. There is this very tiny region in here corresponding to 2.575, and way, way over there is our 8.974. It's very in the critical. I was thinking that because the standard deviation was so large, 3,900, that this would not be in the critical region. But I forget your n is 100 samples, right? 100 samples consistently say that it is bigger than 20,000, then, you know, you bet it's bigger than 20,000. Can't just be random chance. Or if it is random chance, it's really, really rare. We mean say in here is that we have enough evidence, or rather, we are pretty sure that we are more than 99.5% correct. This is the conclusion to be had. Two. We keep going. For three. For three, in the American Heart Association journal, Hypertension, cool journal for this thing, researchers report that individuals who practice transcendental meditation lower their blood pressure significantly. Okay. A random sample of 25 male practitioners meditate for 8.5 okay per week. 0.5 hours per week with a standard deviation of 2.25 hours at a level of significance of 0.05. Does that suggest that on average, men who use TM meditate more than 8 hours per week? I was looking for a blood pressure thing. Let's just work with these values then. We have a random sample of 5. Then we have 8.5 hours per week. That is their sample average or sample mean. 0.5 hours per week. Then they have a standard deviation of 2.25 hours. Notice now, I'm not putting yet sigma or S because we have to understand where this is coming from. A random sample of 25 male practitioners meditate for 8.5 hours per week with a standard deviation of 2.25 hours. Note that the researchers do not say anything about there being the population standard deviation. Note that they are not saying anything about the population in here, that this is just standard deviation of their sample, which means this is actually letter S. From here now, we say, oh, S we're talking about, we're going to have to use the t-test. We're going to have to use, of course, mu, our population, or rather our tested population should be, I think this is enough. Oh, right. The level of significance is 5%. There you go. So let's try immediately. Let's go ahead with the t-test. X bar minus mu all over S per square root of n. Notice as well that the sample size in here is not that large. 25 people is quite large, but it's not something compared to n equals 100. For more and more values of n, you can bet that the distribution becomes approximately more normal. Right? This is what we learned essentially in the central limit theorem, if we remember that in the sampling lecture. So now we have our test statistic. For B, we will now have our our hypotheses. Of course, our hypothesis here, ours, our alternative hypothesis, on the other hand, is on average more than. That is the keyword or key phrase here, meaning this is another one failed test. Letter C, we will have our level of significance 0.05. Letter D, critical region means that this is the one side, specifically the right side, because you're talking about more than 1.645. You don't understand where I pulled that out of, it is the same thing here, because earlier the two-tailed test, aka we don't care if it's bigger or smaller, gave us a level of significance of 10%. Ginawa natin is we cut that in half. Turns out 5% on one side, 5% on the other side. The magic number is 1.45, which we'll be using. Letter E, just do it. Oh, wait a second. Not Z test. This is the T test. Okay. That means we're going to have to go to this table right here afterwards, the critical values for the T distribution. We'll choose alpha of 0.05. That means that for degrees of freedom of 24, okay, here, your V is equal to n minus 1 as per the suggestion, the help, and here V equals, that means we will have 25 minus 1, which is 24. 4. In this case, 24. Go up until 0.05, 1.71. Notice, mas lumaki siya. Right? Let me actually write down the Z value so you understand that that is not correct. Instead, what you need to do, you account for the fact that you didn't interview that many people, right? Or that you didn't have that big of a sample. You're gonna have to account for that by being quote unquote more, and in air quotes. Notice as well that you're not even sure about population itself. You only have here standard pop sample standard deviation. So you have to account for that uncertainty as well. This is what we'll be looking at. T equals 1, or rather, be bigger than 1.7. We'll have 5 minus over 2.25 divided by square root of 5, which is, we'll have a value of 1.1. So, in this case, this is not enough. For F, our conclusion is fail to reject HO. Because, say for example, even if we don't know what the T looks like for 24 degrees of freedom, we still can kind of think about it based on this representation here. There you go. We have essentially a critical region here of 0.05, and apparently this is 1.71 for only, right? At 1.1, this is not enough, okay? And just so you know, these kinds of visualizations, they don't need to be here. They just help me. Maybe they can help you for the t-test. If you were a little bit confused earlier as to what I meant by uh, we don't know what the t-test looks like, it's because there's not even uh, there's not even a function that is supposed to tell you what's going on that is taught to you guys at this level, of course. Right? There is a function, but it's obscured. But they just want you to see in here are the critical values so that you can perform these hypotheses. Notice that if you approach infinite degrees of freedom, it's gonna become very, uh, very, what do you call this? It's gonna become very, very uh, familiar. There you go. 1.645, which is essentially the same thing as our Z test. Because the more samples you get, the more approximately normal things continue. Number four, experience indicates that the time required for a high school student to complete a standardized test is a normal random variable with a mean of 35 minutes. Okay, they're just giving it. They're just giving it to us that it's a Z, the mean of 35 minutes. A random sample of 50 high schools took an average of 33.1. Wow. Average of 33.1 minutes to complete. Standard deviation of 4.0 minutes. At the 0.05 level of significance, 35 against the alternative of less than 35. So now it's less than. Right? Here, we are being told specifically that this is a norm random variable. Even if even if it seems like the standard deviation in here is 4.3 minutes just based on the sample of 50 high schools, we can say that we know enough because they said it for us. So, if you would like, we can also do a little comparison in here. For 4, we will have a mean 35 minutes compared to your X bar, which is 3 point, oh, sorry, 35, not 3.5. 35 minutes compared to 33.1. Our sample in here is then 0.05 level of significance. The thing that I want to test or the thing that I want to compare is, say, for example, if we know that this is a standard, uh, uh, the normal random variable, that means no sigma 4.3. If we don't know that fact, right, we would treat this 4.3 as just our sample standard deviation. So now, I would like to do two tests. Right? We know, of course, that this is going to be a Z test because they specifically told us that this was a normal variable, normal random variable. Oh, but I would also like to test out possibility of this being a T test if in case it doesn't pan out. You can see here, the computation is the same because we're just pulling out the same values. Will be different though is of course the critical region because we have to account for the uncertainty in there. Right? For letter B, we will have our hypothesis. So, and one for your H0, we will have a mu of 35, and for H1, it is less than 35. A one-tailed test. Your level of significance is still 0.05, and then for letter D, this is where we're going to again diverge. Your critical radius, your critical region should be 0.05, which means this is now going to be less than negative 1.645. Notice that because less than, we're now getting the negative side. And the same goes for your t-test. But now we can see that the degrees of freedom are different. because this is 51. Wala tayong -1 in here, which even more so dictates that this really is a normal distribution. Wala, there's no 49, right? And it becomes a little bit of a chore to make it such that it hits 49. As you can see in here, this is your degrees of freedom. Ibig sabihin, higher and higher samples becomes more and more of a normal distribution talaga. Okay? It appears that we cannot even do this comparison. Something, something close to this. Now we do our now we do our calculation. Letter E, 33.15 all over 4.3 divided by square root of, get negative 3.1. Okay, negative 3.12. This is indeed less than negative 1.645. Means we will really reject null high. Seems this amount is enough for us to reject the idea that 35 is the average. It appears that these students are faster at completing the standardized tests. Now we will go number 5. Amstat News on December 2004 lists median salaries for associate professors of statistics at research institutes at liberal arts, other institutes in the United States. Assume that a sample of, oh my goodness, 100 associate professors from the research institute, an average salary of 70,750 pesos dollars per year, standard deviation of $6,000. Assume also the sample of 200 associate professors from other types of institutions, an average salary of $65,200 with a standard deviation of $5,000. That's the hypothesis. In salary for associate professors research institution is $2 higher, $2,000 higher for those in other. Use a 0.01 level of significance. There is a lot here going on. All right, let's try this out. Assume that a sample of 200. Let's start with this. One is 200. Then they have a X bar 1 of $70,700 with standard deviation of 6,000. 6,000. Now notice what kind of standard deviation is. I am inclined to say that this is an S. Same time, look at your sample. It's 200, and notice that the T table goes up to 120. So it appears that right now we know, quote unquote, we know enough to say that this is representative of the population. And malaki ang sample, we can say, all right, this is our population standard deviation. Other hand, 200, well, we know 2 here, this is going to be 5,000 to 5,000 with a population standard deviation of 5,000. Yes, 5,000. Now, use a 0.01 level of significance. All right. Suppose we could also just put in here our assumption, or rather the thing that we want to test. Test the hypothesis. The mean salary for associate professors in research into $1,000 higher. Okay, 2,000 is our magic number, enough for us to get our test statistic. If you're boggled by all of this, you can just consult the help sheet right here. And it seems that when both sigma 1 and sigma 2 are known, the distribution is this one, the z plus again, like the t-tests for this big of a sample. Z-test right here will be R1 minus your difference all over omega 1 squared all over n1 plus omega sigma 2 squared all over n2. That is all over, all inside of your square root. So that's your test stick. Letter B. Now we will have our null hypothesis and our alternative hypothesis. Here we know, or rather, we are assuming that nothing happened, aka this. Oh, sorry. This is our case. U0, our H0 is such that the difference is just $2,000. Here we are saying that in the alternative hypothesis, it is bigger than, more than, or higher than $2,000. Letter C has level of significance of 0.01. Letter D, our critical region now, should just be the for a one-tailed test, 0.01. I don't think we've seen that before. Scroll back 0.01. This one, this one here, negative 2.32, negative 2.33. I will just cut that in half. I'll say negative 2.325. Notice that I am basically just looking at the negative side of things here. The positive side, mamaya maguluhan pa kayo. Okay, for me. What I just remember is the fact that the normal distribution is simple. So these things on the left side also work for the right. So, go. That is your z. Z is bigger than 2.325. Let's just come. Okay. 70,750, 65,000 minus 1,000 all over square root of 6,000 squared divided by 200 plus 5,000 squared divided by C. This gives us 100,000 square root of 1,000 squared over plus 5,000. We will have our answer, which is 6 point. Oh, there you go. 6.428 or 6.43. That is enough to say that this is reject. The null hypothesis. Yeah, if you just take a difference, this is gonna be way bigger than 2,000. Maybe they should have said 5,000. I don't know. But yeah, it's pretty clear to me that even without hypothesis testing, it is bigger than 2,000. Hopefully, you guys are answering this. Find out whether a new serum will arrest leukemia. Arrest in this case means slow down or to stop. You're under arrest. You're stopped. Will arrest leukemia. 9 mice, all with an advanced stage of the bad, are selected. 5 mice receive treatment. Survival times in years from the time the experiment commenced are as follows. That is group. 0.05 level of significance. Can the serum be effective? Assume the two proportions to be normally distributed with equal variance. All right, in this case, we have really small samples. Let's have ones without we'll have N1, which is 5, got the treatment. Currently, we're going to have to get the average and the standard deviation of this because, well, this is all we've got 2.1, 5.4.9. We can get them by using our calculator, of course, right? From here, we will get your X bar. Apparently, the X bar in here for ones with treatment are 2.86 years. And their standard deviation, S1, going to be 1.9705. I think this is good enough. Note that, of course, because this is just what, like 5 and 4 samples, we have no clue what the population is like, and will not have a clue what the population is like because only 9 mice are selected. See now, your N2, we will have 4 samples. Reset, calculate. 1.9, 0.5, 2.8, then 3, 1. Let's get, here is 0.07, 0.07. Here's, see our standard deviation is 1.7. Now, we have more info on the bottom, of course. The level of significance is 0. And we are, the two populations are normally distributed with equal variances. That is the big key phrase here. They have equal variances. We'll just use, pooled variance. When you know that the population standard deviations are the same without knowing their value, we just assume the pooled variance. If you want to see this, looks like a weighted average. Looks like a weighted average. What do you mean a weighted average? Note that this is the number of degrees of freedom for the first. This is the or degrees of freedom for the second set, and the bottom is actually just an addition of them. Addition of the 2 degrees of freedom. So if you want, you can think about it like you can see in here that the degrees of freedom for the first set is 4, second set 3. We can get our pooled variance here. SP squared is going to be equal to 4 times 1.7 squared plus 3 times 0.17 squared all over 4 plus 3. Give us a value of, could have saved more decimal place, but it's whatever. 0.97 squared plus 3.1, 3 times 1.16 squared all over 4 plus 3. We'll have 2.801 for our variance, which means our pooled standard deviation is actually gonna be equal to 1.674. 0.6737, I'll do 1.4. Now have our test statistic in here, which is a test, of course. Of course, it's gonna be all. The test is this. This now that we have pooled standard deviation. So we R1 minus all over SP times squared of 1 over n1 1 over there b we will have our hypothesis, and this one is a little bit more difficult. Why? Because they want us to test, can the serum be said to be effective? What does that mean? Do some critical thinking. What is this serum supposed to do? It will arrest leukemia and make the mice longer. Then what? If they're supposed to live longer, then the amount of mice, or rather the average lifetime of the mice who take in the treatment should be different, should be bigger than survival rate of the mice that did not have treatment. In other words, mu1 minus mu2 is 0 for this one. In this case, mu1 minus mu2 is bigger than 0, aka mu1 is bigger than mu2. In this case, treatment is better than without treatment. That is what we want to test. C, we will have a 0.05 significance. Letter D, we will now have our critical region. Note that this is one-tailed test. One-tailed. Now, what we will have is our T score, our critical T score. Note in this case that we will have a pool variance with an addition of the two standard degrees of freedom. Add 4 plus 5, that is 9, minus 2, that will be 7. So it's 7 and we just add 4 and 3. 7 down and 7. Then bigger than, right? Bigger than 0.05, that will be 1.85. Let's see, really does work. 2.075 minus 0 all over your SP is 1.64 all over times square root of 1 over 4 square root of fourth plus 1. Our answer is 0.61. That is not enough. Means, sadly, we failed to reject our null hypothesis. There's not enough of a significant difference for us to say that this theorem works for 6. You have to pick up on those you have to pick up those very tiny phrases. Can the serum be said to be effective? Many students have had Many students have had the unpleasant experience of panicking on a test because the first question was exceptionally difficult. The arrangement of test items was studied for its effect on anxiety. Following scores are measures of debilitating test anxiety, which most of us call panic blanking. Is there sufficient evidence for the claim that the arrangement of the test items score significance level of 0.01? We have 25 samples from easy to difficult, and we have 16 samples for difficult to easy. Now, 25 and 16, that is not big numbers. Those are not big numbers. We can think, we can say that this is gonna be a t-test. What kind of t-test? So if we read the question again, nothing said at all about the standard deviation. Nothing said at all about the standard. So, sorry, we can't assume about the variances at all. Say that maybe one of them more order than the other. When you know that they are not the same without knowing their value, we can use the pool degrees of freedom. Yeah, get it. This looks horrible. But you have this written down or quiz help. I will print this. I will give this to you if you would like. Let's just try this out. We first also just enter the values we will have in here. set 4 points. You can skip this if 4 point 16.32 7.0. Oh, this guy did not, or this person did blank out apparently. 31.73 20 32 6 30 point 30 point 28 point 30 point. There we go. 25 items done. Let's just have our new X right here. That is 27.1152. Then our sample standard deviation is 6.857. The other hand, for your X2, set 33.34. Go up to bottom. 35.7.4.32 440. Very, very stressed. 6.60 49 30.2 30.35.33. Those are 16 terms. Our X bar now is gonna be 31.72. Whatever. That's enough. Then for our sample standard deviation, we 4.0, 4. So that's why I can't say that these two supposed to have the same standard deviation. That's why we're going to have to really get computing based on the Welch Satterthwaite equation. Yep, Welch Satterthwaite. The fun fact, person Welch is the same person who's done the t-test. That's cool. 16 minus 1 is 15. So what we will have in here now is our pool degrees of freedom, which is going to be gigantic thing. Write this here. Have our values here. S1 squared 6.857 squared all over your N1 plus 4.260 squared divided by 2 squared all over squared over squared all over N1 minus 1, which is 4, plus do the same thing, 4 point squared divided by squared over N2 minus 1. This happened. Over 24 plus 4 point calculator divided by squared. Got 38.98, which what you're supposed to do with this once you're done, you round down. 38. 38. Very close to 39. Anyway, all of this, and we haven't even finished yet. We haven't even started yet. Our test statistic should be bar 1, bar 2, all over. Gonna look here. S1 squared over n minus all over n1 squared all over squared over have. Oh, sorry, getting ahead of myself. Letter B. Of course, we're trying to understand if these two different. So 1 minus is 0. Then mu1 2. Let's try to see if it is two-tailed or one-tailed. Is there sufficient evidence to support the claim that the arrangement of test items influences the score? Notice that they don't say anything about the kids makes the students more anxious. It's anxious. You're just saying if there is influence. It could be a positive influence, it could be a negative influence. Therefore, therefore, it's a two-tailed test. Letter C, we have uh call this a significance level of 0.01. I can already see a problem right here. Letter D, our critical region is going to be very, very impaired. Why? Because it goes up to 40. We can do is we can round up to 40 because that's the closest thing to 38. But here's the other thing. It's 0.01. There is no value here for the oh, meron pa pala. Okay, there 0.01. So never mind that. But what we need in here is a two-tailed test. So what you're actually going to do is that you're going to split that up to 0.005 because at 0.01 cumulative. Dapat meron siya on one side and the other basically splits it even lower into 0.005 territory. So your t-test needs to be here 0.005. Let's just try 40. 2.704. Either your t is bigger than 2.704 or your t is less than negative 2.70. Out E. 31. 31. Sorry, 27.11. 31.72 minus 0 all over s squared 0.8 squared all over plus 4 point squared all over 16 out square root point squared all over plus 4 point squared all over. We'll have an answer of oh so close negative 2.6565 2.66 negative 2 point sad but it is out of our critical region. Not enough say that the test, or rather the arrangement of difficulty, the test questions, sorry, the or order of difficulty test questions is enough to generate more or less anxiety within. Although it was really close. If this were if this were a one-tailed test, if they were a little bit more specific about this, it would have passed. It would have passed. Your number 7, and for the last three, I think yeah, we're gonna have tests on proportions. I remember doing this. We're doing this, not this, this, and this. Those are our last three. Marketing expert or pasta making company believes that 40% of pasta lovers prefer lasagna. If 9 out of 20 pasta lovers choose lasagna over other pastas, what can be concluded about the expert claim? 0.05 level significance. Here again, there's mention about than or than. Therefore, you're gonna default a two-tailed have here 40%. 40 have a number of people 9 out of 20 means that their p hat, right, the estimate for the proportion is 9 over 20, which is 0.45. Now we will have in here is we can make our, you call this, we can make our mean, can make our variance as well, but I think enough because this is one population. One population, we just need this, the z test. If you remember, that is our test. Will have your p hat, p all over your p hat divided by, yes, I get that. Oh, p o q o divided by. Right. Okay. So letter B, there's nothing being said, so your population gonna be equal to your 0.4. Not population, it is proportion we're talking about. Therefore, the alternative in here is not 40. It could be bigger than, it could be smaller than, basta hindi 40. Letter C, our alpha in here, our level of significance is 0.05. Hahatiin yan. Letter D, our critical region should be twofold the test. That means we're gonna have to look at values of 0.025. Natin. 0.025, exactly. This one, negative 1 point. It could be bigger than 1.96. Could also be smaller than negative 1.6. Do our calculation. 2.45.4 all over square root of 0.4 times 0.6 divided by 20. Divided by, you will get an answer of 0.45. Okay, there you go. Ernest, this is quite a small difference and quite a small sample to 20. But go. That's our conclusion. Our conclusion is we failed to reject null hypothesis. There's two more left. Both of them are still proportions. Suppose that in the past, 55% of all adults favored capital punishment. We have reason to believe that the proportion of adults favoring capital punishment increased. There you go. If in a random sample of 10 adults, 8 favor capital punishment, 0.05 level significance. So, for 9, our proportion should be 5%. But you can say that 8 out of 10 adults, a big estimate of 0.8, 80% is we'll see. We temper this because the n in here, the sample size is quite small. Okay, but still, this is proportions we're talking about. So p hat minus over square root of pq divided by n. Under b, we will have our null hypothesis, which is just p is equal to 0.55. We're now testing if it is bigger than 0.55. P, our level of significance is 5%. Therefore, letter D, our critical region, should be such that Z is bigger than 1.645. This is the same thing that we've done in number 1, if you guys remember. Letter E, let's just now equal to 0.8 0.55 all over 0.55 times 0.45 divided by 10. Yes, it is 10. Pero, oh, we'll have an answer of 1.589. Wow. Wow. Huh. Believe that. Really? Okay, sorry. Yeah. Believe that because our conclusion, we failed to reject. Wow. Okay, and I'm a little bit in disbelief because the difference is so wide, 0.55 and 0.8, but apparently because we only have 10 samples, thing is we can't rely a lot based on this value zero point 0.8 because maybe they really just picked more people who are in favor of capital punishment. Even if that proportion is quite high, could have picked another different 10 people. Proportion would now be much low. But apparently, because 0.589 is smaller than 1.645, that really is not enough for us, not enough evidence for us to suggest that this is bigger than 0.55 as a proportion. Now, finally, before we go to variances, which is next video, we have number 10. In a study to estimate the proportion of residents in a certain city, suburbs, favor the construction of a nuclear power plant, it is found that 63 out of 100 urban residents favor the construction, while only 59 out of 25 suburban favor. Is there a significant difference between the proportions of urban and suburban residents? Now, notice they're not saying one is bigger than the other, one is smaller than the other, is just for differences in proportion. Is there a significant difference between the proportions of urban and suburban residents who favor construction of the nuclear plant? Use a significance level 10%. 10%. Let's write that down first. 10. We will have for your urban, X urban is 3, urban is 100. You will have proportion for the urban to be 0.6. On the other hand, for the suburban, we have 59. For the suburban, we have 105, which means it's going to be equal to 0.472. Right now, we are seeing that there is a difference, or rather, that's what I can see. We can also have this pooled proportion. Pooled proportion, if you are going to know here, this is the only proportion test that we have, of course. Here, the pooled proportion, there are P hat and Q hat in here without any subscript. That is just a pool. All of the successes over all of the samples. Here, you can have 3 all over 100 plus 105 is 0.54, 0.54. Okay, now let's try this out. Of course, there's only one test statistic available. D is gonna be square root of at 10. About this 1 over n1, then plus 1 over n1. So, after B, you're just testing for differences. Not saying that urban is gonna be bigger than suburban, so on and so forth. That means it's a two-tailed test. Letter C. Our level of significance is 0.05. 0.10 pala. Okay. Sige. And that means that for a critical region, I can just reuse the same thing that I've seen because this is a two-tailed test. Hahatiin siya sa dalawa. That means that this corresponds to a 5% level of significance on both sides, aka copy this one. 1.645 in here, or less than negative 1.65. Now try this out. Letter will have 0.6, 0.472 all over value 0.54 times 0.4578 times 1 over 100 plus 1 over, see this, 100 will have 2 point there, 2.364. 3637 or 364 is enough because we can finally reject that null hypothesis. You can see that, well, I can see that these two proportions are quite different. I am quite parang confident because the samples are quite large. 100 versus 125. Granted, they're just saying one thing or the other. Either I support or I don't support. But still, this is quite a good enough tool for us to just determine whether we are most likely correct or not. So all of these 10 questions to stick around with me for all of these 10 questions. Notice that at some point we just stopped doing visualizations because, hopefully it's already within your brain. Well, we will be doing lots of visualizations later on, though, for variances. The variances that's gonna be lopsided. Lopsided, but I mean is no longer, it is no longer symmetric. You guys then for that final lecture. Maybe you can watch it on Friday if you make that your final lecture for the subject. But thank you very much. I'll see you